First of all, I just want to say hi to everybody. It's very nice to be here. I have attended multidimensional chromatography workshops before when I was in my PhD program, and it's very nice to be back to present more from now being part of Mark's SEPSolve. So today I'll be talking about integrating GCO with GC-GC and some of the sample enrichment. So just in case you don't know what SEPSolve is, so we are more on the modulator, TOF, and chemometric side. Our sister company, Mark's, is more on the sample introduction side with the thermal desorption and sample enrichment, also the sampling technology part. Now, both the companies, as of last week, have been bought by the Valerius Group, so that's what we belong to now. We have offices in North America, here in Sacramento, and up in Canada in Waterloo, also in Germany and China, with, of course, our headquarters in the UK. So SEPSolve has been, part of the separation technologies from when the first benchtop came out in 2008. Since then, there's been many updates to the TOF with the new source design and the transfer line coming out just last year. We also have a flow and a cryogen-free thermal modulator. But really, I want to highlight some of the most recent things. So one of them is that in 24, we have acquired Hyperchrome, which is a fast GC invented by Peter Becker in Germany. And we also launched Smart Subtract as part of the Chrome Compare, and I'll be talking about that a little later in my talk. So, as we know, GC-GC is great for aroma profiling. As you can see over here, we get hundreds of peaks that it really are most suited for a GC-GC. If you look over here, we can see if we zoom in, there's multiple peaks overlapping, and so we need that second dimension separation. Further, if we look at a 1D, we can clearly see that if we were doing only 1D chromatograph, we'd have multiple of analytes overlapping. And what that means is that if we're looking at the flavors or odors that are coming off of these samples, some of the less concentrated things, specifically, some of these nutty and oniony flavors would be kind of not picked up because if we're smelling the sample, really the fruity and the vegetable aromas would be just kind of just so concentrated that that's what would be picked up. And so going from that, really the question is how are we going to correlate this chemical data with a sensory experience? So when we talk about traditional GCO, there are a couple of challenges. One is the low odor detector limit. So our noses are the best detector that there is. Potentially the mass spec might not be picking up the things that an analyst with an ODP is. The other thing is the co-eluting compounds. If we think that we're perceiving an odor, we might not know that it might actually be multiple analytes that we're perceiving at the same time. So in our studies, we have done, we've integrated Phaser Pro detection port in a regular GCO setup. This would look as a sample going into a GC column, and then at the splitter being split between an ODP and the detector. Then as the analytes are coming through, a person sniffing at the ODP can then select what they are smelling, and then that correlates back to a chromatogram so we can see the chemical data. But what happens if, what happens if a person is smelling, let's say, an apple smell but there's nothing coming out in the chromatogram. What can we do then? Well, we are solving that by adding a Sentry system or sample enrichment at the beginning that helps us pre-concentrate the sample before it hits the GC or later on GC-GC. This helps us enhance the detection limits. So the way that the Sentry works, in case you're not familiar, so our Sentry system allows for regular sample introduction techniques like headspace or SPME arrow. We also do have Heisorb, which has more phase than a SPME arrow, and we can also use tube-based TD. All of these samples, in whatever way, get desorbed onto a trap that is electronically cooled, so we are not using cryogen. And all those analytes enter the cool trap. The nice thing about this is that we can actually repeat injections onto the trap. So while the trap is being cooled, we can do, let's say, 3 SPME injections onto the trap. Also, because of our specific trap design, we are using multiple sorbents, so weak, medium, and strong. So your biggest analytes would actually get stuck kind of in the weak sorbent, while the lighter analytes would go all the way to the strong. And then when we are desorbing, we do that in the opposite direction to ensure that everything gets off the trap. The trap is ballistically heated up to 100 degrees a second, meaning that we're going to be moving a very narrow band into the GC. This potentially, even if you do not do the enrichment portion, helps a lot with narrowing the peaks when they come off of like a SPME fiber. Additionally, we can do an automated recollection before it goes to the GC. So if you're thinking about food samples that potentially can go bad, this is a good way to capture them onto the TD tube and preserve those samples. That also works with anything that you have very limited amount of and can do only so many injections. You can just preserve that for months. All right, so now that we solved the issue of limit of detection, and let's see, we are now able to see the peak for the apple smell. The next thing is, what if there are multiple compounds that are coming off at the same time and the analyst is smelling a sweet smell and that's all that there is to it? Well, what we have done is actually put a flow modulator to the line that's coming off of the splitter, and then that has a 2D column, and then that hits the detector. So that allows us to now see that the sweet aroma is actually put together from 3 different compounds in this specific case. Now I'll show you a couple of preliminary studies that we've done with the setup. So one of them is doing the citrus rinds in an empty TD tube. If you're not familiar with TD, I do have some TD tubes that I can show you on how they look. But anything small enough to fit into a TD tube, we just can do it thermal desorption. So you can do it at different temperatures to see what analytes come off. In this specific case, those go into our auto sampler and then are moved onto the trap the way that I've described previously, and then are analyzed by the GC TOF. You can see here we get a quite complex chromatogram, and we can see how where some of these analyze specifically, like the woody smell that a person is identifying on the ODP is actually put together by multiple things. So to show you that a little bit more, we can see that while somebody is smelling a woody aroma, there is actually another compound in there that has a small, like, caramel-like smell. From here, we also have analyzed orange juice with pulp and without pulp. This is done by the Headspace Heisorb extraction. So the Heisorb probe specifically here is the one for the Headspace. We also have a longer one that is immersive. So we can do kind of, we have a wash station and a dry station, so it actually allows us to do immersive, while with like SPME, you'd struggle with that because of all the sugars in the sample. If we look at the chromatograms first in a 1D mode, we can see that there's really hard to tell what the differences are, and also they're complex enough to where it really does need GC-GC. But if we specifically are looking through the things that are appearing in these, we can see that we get some citrus, some herbal, some floral smells, some fresh smells, some piney ones, and then some leafy. And we can see that all these peaks are kind of showing up in both chromatograms, and really you need to look really deep down at one of these peaks over here that an analyst with an ODP identified as a woody flavor that does not come off in the without pulp sample. Further, this is how it looks in the two-dimensional mode, which looks much better. Everything is much more separated out. Again, if we zoom in kind of that same portion, we can see where those aromas were coming off. And then we can see what actually was contributing to that woody aroma. Another one to kind of note is the nonal over there that really would have been covered by some of the other peaks if we would just been running a regular GCO. So from there, I want to go into very slightly on the chemometric side. So if we're just looking at those two chromatograms, it's hard to tell what's different. And usually when we're comparing just, one chromatogram of one type and a different chromatogram of a different type, the one thing that comes to mind is just to do a regular subtraction. However, that will come up with everything that has even small differences. So we have come out last year with a chemometrics-based smart subtraction, and in this specific example, there was actually only one compound that was spiked, and it performs very well at actually just picking out the things that are actually changing. Now, when we do that for the pulp versus no pulp example, we can now clearly see where the differences lie, and that there are actually quite a bit that we visually just couldn't see. Specifically to look at what compounds there are multiples that actually have flavor profiles. So the furfural has a nutty almond flavor. The furan, the dimethylfuran will have a coffee-like aroma, and the generality lilanone will have more of a floral flavor. And so with that, the GCO is an indispensable tool. It is used throughout the food flavor and fragrance fields a lot. And here we are showing how using a trap-based enrichment helps with, with the limits of detection. And then GC helps to make sure that the things that an analyst is smelling, what analytes are actually in those smells. And then just to kind of note, our Waterloo lab is going to be moving 10 kilometers down the road into a much bigger space. And Matt Edwards is very excited to see everybody there in May with the opening. It is going to be a lab that will have both Marks and Sepsolve equipment now. And with that, I'll be more than happy to take any questions.